path independence of the vector field. Something like that, I don't know, whatever. And you picked your origin here.
Yeah.
And you're trying to,
Oh.
you're trying to find how the potential, you wanted to find the potential in this set. Well, then the trouble is like
Yeah. Discontinuity.
you're outside of the set if you're not careful, so you can't, right? So if it was something like this, if you had path independence of the vector field, you'd want to just say that the potential is defined by just integrating any old curve from there to there, and like that single value, because you're assuming that your vector field is path independent. But then the question is, okay, so I define the potential by integrating this path independent vector field. How then do I know that this path independent vector field is such that that the partial derivative of it with respect to x gives me p, and the partial derivative of y with respect to y gives me q. In this context, right?
Mm-hmm.
And then the game becomes to take this curve and say, okay, well, if it's open and connected, I can always get basically close enough to the curve, and then like, okay, I can take this curve and I can replace it with something that goes to here and then does like an L. I can always get this L curve as like the terminal thing here, either by going below it or above it or some different which way. I can approach it with this like generic L path close to the point. So what I'm trying to say is I think you could just like make a little topological adjustment to the proof and then fall back on this argument as the end game to it. But then it always begs the question, like the point where you make the L, does that depend on this point? And I think if you can convince yourself at that point and the point where you start the L are independent, or I don't know, I told you about this before, there's something about this proof that I'm still not quite 100%.
What if you change, like,
All of that said, it's okay if we're rectangular. If our domain is rectangular, then like whatever sort of topological shortcoming I have in terms of the nuance of this kind of proof, it doesn't matter because.
no, yeah, because I was, what's the one, can we decide what the orientation is? Of horizontal and vertical on the set? Or is it already defined?
In R2, I mean, it's
Defined, yeah.
it is what it is, I guess. Oh, now on A cross A.
No, see, that's, my thing was like, what happens, like if it wasn't defined, there's a point where like, unless you cross over, that's the only problem you get, you start crossing over. But you could find a point out here, you could have a 90-degree angle, and then consider that vertical, and consider that.
Yeah,
That's what I was saying, like how rigid is the definition of vertical and horizontal?
I mean, I think they are what they are in the
R2.
Yeah. So, all right. So set aside my worries for a second about how to adapt this to non-rectangular domains. Suppose we're in a rectangular domain, Let's go forward with the argument here. He says first the integral is he said the first integral is independent of y. Like, okay, I'll buy that, right? I'm going to erase this so I don't have the temptation to talk more about it at the moment. we'll have to come back to that as we think more about this, but that's independent y. So the question is, if we're trying to differentiate f with respect to y, what should we look at? Well, he says, okay, so partial f partial y is partial y of the integral from y naught to y of q of x comma v dv, right? And he says, okay, well, basically by fundamental theorem of calculus part 1, since we're differentiating an integral with a variable limit, we just take the integrand and evaluate at that. So we get q of x comma y. Hey, that's half of what we need, which is that, you know, partial f of partial y is q, right?
Mm-hmm.
Our goal is to show partial f. This is a target. We want this. Did she take the mixer somewhere else? I think she took the mixer to the guest room. Well, thank you. All right, so that's half the battle, right?
Yeah.
All right. Now he says differentiating f with respect to x. We have what? X naught to x, p of u comma y naught du, partial x of the integral from y naught to y of q of x comma v dv. That's what he writes, right? Now he says the first term is p of, what is this one here? So again, by FTC part 1, this guy is just p of x comma y naught.
That should.
It's not quite what we want. We need p of x comma y, right?
Yeah.
Now what he says next is he says that the second term, the variable x appears in the integrand, and he says it can be shown that since q and partial x are continuous, that you can commute the integration and the differentiation. So he uses a result of advanced calculus that because of the continuity of the partial derivative that's assumed, that you can he says, okay, well, because of analysis that we're not actually showing the details of here, right? we can rewrite this as the integral from y naught to y
Lost you.
sorry. Goodness gracious. Ow. Not bad.
Well, that gets rid of our v, and we're left with q of x.
So we get partial q, partial x at xv, right? Now we can use the fundamental theorem of calculus on this. excuse me, not the total theorem calculus, but this is the net change theorem, right? Oh, excuse me. I'm a dummy. What do we now know? We assumed what? Suppose this is that, right?
Mm-hmm.
So,
Oh yeah, partial Q, partial X we can change for partial Y, partial.
P partial y, x comma v dv. So I'm integrating the change with respect to y, so now I can use the net change theorem and say, aha, well that's p of x comma y minus p of x comma y naught. At which point we get to keep the p of xy that we want, and this guy and that guy cancel out. So I would identify, well, I guess there's sort of maybe 3 or 4 critical aspects to the argument here, right? The one is that we can fit this kind of L curve inside the domain which we're looking at. He's assumed it's a rectangle, so that's great. The other, of course, is that the fundamental theorem of calculus part 1 holds, right? That the derivative with respect to an interval variable bound is just the integrand evaluated at the upper bound. The other thing, of course, is that we can commute the integral and the partial derivative given appropriate condition on the continuity of the derivative. And then finally, the net change theorem.
Some of the stuff sounds like it's not in an algebra though.
I don't know. I think it'll work.
Like, does the net change? Have we defined what A cross A into A integration is? 'Cause I know we've done it for A into A.
Yeah, well, I'm assuming that we don't even bat an eye talking about integrals. Honestly speaking, these kind of real integrals, they're really, they're parameterized family of real integrals, where y naught is a parameter, and it's like, y naught's fixed, it's not a parameter. It's like, well, I don't know. Over here, is x fixed, or is it v is the integration variable. But x is not fixed, right? We're varying x over here. X is definitely not fixed. X is a variable. So this is not just one integration. This is a function of x which is defined pointwise by an integral from y naught to y. So I would think that we can think about integrals on A cross A in kind of the same sloppy way. Namely, it's like families of integrals of A integrals. I don't think it's any worse than what we do in calculus 3.
I don't know, I'm not convinced that some of these things hold. Like, first, net change, I think we have to, what is net change over in algebra?
Oh, I think that's the net change theorem essentially is just FTC2.
And that holds over in algebra?
Yeah.
Okay.
Yeah. So because that goes back to the if we go back to my calculus 1 paper at the end of it, it's there. See if I can find it. section 10 on integration. So it's my theorem, theorem 10.8.
10.5, 10.6, 10.7.
See, so this is theorem 10.8. So if you have a curve that goes from P to Q, and you have that your integrand is the derivative of an derivative of the antiderivative of big F, and you take f of Q. I mean, this is FTC part 2 for the algebra. The thing is, if you just write this a little differently, you've got df, d zeta. See what you get. You get the net change theorem. So he gave the proof for a rectangular region, but he stated the theorem for a simply connected domain, I think. It's Alice Neely if you look at it. So simply connected doesn't have to be rectangular, it just means there's no holes, what's interesting about this particular, one of the things that's interesting about this particular proof is that while I drew all right, let me just dive ahead here. I think I know what to do. All right. Oh,
we do have this, season, okay, so, and then from that we have the equivalent that like in the integral of f times dz is equal c1 integral f star dz is equal to c2 f star dz, because it's a closed path, right? From that same paper from your first A.
Oh yeah, we do have the path independence there.
Yeah.
Yeah.
But the example you gave is for a rectangle though, not for a. Does that hold for sets that aren't?
Well, I have a. Let me just try to get out here. So I think the theorem we're after, right, is that we can let P and Q be functions on A cross A to A such that P and Q are twice continuously differentiable. With partial z and partial w derivatives existing. Right. Again, I say that is going to be enough to imply that the second partial derivatives with respect to z and w likewise exist. Right. If not, we can change it to that later. Then, if gradient of f is by definition partial f partial z comma partial f partial w, right? So I'm defining this symbol, all right? Let me just say that for f be a function on A cross A to to A again, all right? Then how was it written before? There exists f such that gradient of f equals to p comma q, right? If and only if partial q partial w equal to partial p partial z. Now you'll notice there's obviously like a gaping hole here. This should be like on blank on blank, right? Like there needs to be the simply connected or rectangle or whatever goes there, right?
Yeah.
So I'm just trying to set that aside for a second and just sketch the proof and show you why we need to think about it. So like proof. Okay, so the one direction, the forward direction, I think we've really sketched aspects of that already. So this basically boils down to that partial squared, p partial z partial w equals partial squared p partial w partial z, right? So, well, I guess I should write f there. That's really the issue, is that f does that, right? So because those commute, that gives you that, you know, this condition, right? Just to summarize that aspect of the proof, I don't want to. We could spend 20 minutes digging through it again, right? But that's not where I want us to focus our attention. So that part I think is more or less pretty straightforward. Once you for sure know this identity.
Yeah.
The other direction though. The other direction is the tough part. So
If you have simply connected, I don't think it's that bad.
So suppose, yeah, but the thing is,
That is the thing.
what's that? Suppose partial Q, partial W, partial Z, right? That whatever, you know, fill in the blank. I don't know what yet. Define. I want to say we can define just like take a page from Salas and Hilly, right, and define big F of Z comma W by this formula, right? Integral from Z naught to Z, P of, I'll do an eta this time, eta, comma W naught, and I'll put a star here to emphasize it's that kind of integral, right, d eta, plus the integral from W naught to W of Q of Z, comma, I guess I'll do what other letter haven't I used yet? I don't know, sigma. Star D sigma or something, I don't know. You could put a zeta here. I'll use zeta. I haven't used zeta for a while. I got my eta, I got my zeta. So let's examine that formula and see what it demands about the fill in the blank. What is that? What do you need in order to write that formula that I just wrote? What must we demand?
That P is Y independent.
P is Y
Or
independent.
not Y, or
I guess I'm
Z
saying
independent.
if we think about these inputs into P and Q, right? What does that say about? I mean, P and Q are only given to us over a certain, you know, context. In the context of Salas and Hilly, they're given over a rectangle in the proof, you know, or simply connected region in other places. But if we just look at this formula, like, obviously W naught has to be in the domain of P, right? Well, what else? Eta ranging from
Z.
Z naught to Z. And then over here, it's gotta have, Q has to have Z points with Z and also W ranging from W, zeta, you know, this ranging from W naught to W. So if I draw kind of a picture of it, I mean, you can, if you want to, this is a very heuristic picture, right? So this is like W, this is Z. I'm just drawing this as sort of a heuristic for the A cross A plane. You know, there's this point. I mean, it's that picture again. Right? Like that. Line segment, which is I mean, I guess it is a pair of line segments, but in a 2n real dimensional space, right? I mean,
I'm having trouble just visualizing what mappings look like on certain types of numbers, because like, are they always gonna look like that? Like, you remember back in differential geometry when like our map, like, you know, like the hyperbolic space wasn't necessarily straight lines?
uh-huh.
Like, what happens in those algebras? See, like, I feel like if we want generalized, like, simply connected is gonna have to be.
Well, yeah, I think, not Swedish.
Like, if you know, if we have something that's like, see, but that's even fourth dimensional, you know, like, if you have like a H2 and H3.
I mean, we could make our condition, you can make our condition on the set for the theorem, just very heavy-handedly. It's not very clever, but it's always an option. Say, we're looking at the domain, the omega, as a subset of A cross A. It's a set for which there exists a point, Z naught, W naught, such that if we take the line segment from Z naught, W naught to Z comma W naught, well, excuse me, such that for any point, Z comma W in the space, the line segment Z naught W naught to Z comma W naught, and then Z comma W naught to Z comma W is inside the domain. Basically just say that your condition for the domain is that that L in A cross A is in the domain. Now I kind of agree with you. I think you're like, well, that's kind of, you want something that's more sort of less, well, for lack of a better word, tacky. And I do think you're right. We could go back to like theorem 10.9
From ACAL or
from ACAP, from the introductory paper, and like connected subset equivalent. I mean, I do like the idea.
Well, we know that, you know, for number 3, we say there exists an f such that df d zeta equals little f on u. I say that because if we know the derivatives exist, we know that that big F exists. Because, you know, all we're saying is that we have partials. And to say that, you know, and if big F if 3 holds, that means 1 holds, that means it's simply connected. I'm trying to find the paper. Don't give me the ring of death. I'm talking about 10.9. Because we equated that 1 implies 3 and 3, and you can go from 3 to 1.
Mm-hmm.
And so if you have 3, which is what we're saying, I mean, you have 3, that there's a P and a Q that have angular derivatives, which df of d zeta equal a little f, in this case a Q or a P, on the U. But
we have 3 so
yeah. Because P and Q are derivatives of f. Another partials, I don't know if that holds for partials.
No, we don't have F though, because we just have the partial of Q, partial W equals partial Q, partial V.
says, so 3 says f has an antiderivative of big F, for which df of d zeta is equal to f. And then we have a big F for which these two intervals.
And we're defining big F by those two intervals.
Yeah. But 3, we have here that 3 implies 1, and 1 is saying that, u beginning and ending at the same point. And so wouldn't that imply that, doesn't that imply that's simply connected, meaning we can always have an L-shaped figure?
But again, we haven't proved yet that we have a big F such that the X is a little F. What I'm trying to say is you could, there's an interval we haven't defined yet. So, think about this.
But if we have 1 on 10.9, that means we have this L, right? So we can always have this L.
Well, I guess the question is, if the L fits inside the domain that we're supposing the condition, I mean, we need the L to fit inside wherever these conditions are given,
Yeah.
because that's the secret sauce to make the calculation I just erased go through.
Yeah.
But I would like to, okay, so you could instead just sort of define this, right, as, in the real case, you could replace this with the interval from this to this of p comma q dot dr, right? And path independence says that it's equal to the interval over the L.
Yeah.
Provided that you can perform the path to the L, which is the thing that's simply connected and give you.
Yeah.
But what I'm trying to get at here for just a sec is that if we have a curve, sorry.
There you go.
It occurs to me that it's not been yet defined what we mean by this in the curve, which is a subset of A cross A.
Yeah, and okay, so here in theorem 10.9, it says, let little f be u to A, but it says u is just a connected, never mind, 10.9 doesn't even mean anything because we're talking about u as connected subset of A, not A cross A.
Yeah.
So that kind of gets thrown out the door.
It's okay. So this is what I'm saying is part of the interesting aspect of looking at this problem is it challenges us to think a little bit about how would we do calculus on the A plane, the A cross A space, right? And one thing you can think about is this would be a vector. You can think about this as a function from A cross A to A cross A. Some people think about vector fields as actually just functions from Rn to Rn. The vector field on Rn is just a function from Rn to Rn. Because for each point in Rn, you attach a vector in Rn, Anyway, my point is here, if this is a curve, well, we can think about you know, alright, so suppose that T naught to say T1 maps up to there by, you know, pick your gamma is the name of the parameterization, right? So like, so gamma, it's going to have two things. It's going to have the Z component and it's going to have the W component, right? Because it's a mapping into, this is a curve in A cross A. So, I would think probably the thing to do would be integrate T naught to T1 of, you know, P gamma T. And then it's gonna be dz dt, you know, plus q of gamma T dw dt. I would think that's probably the definition of the line integral in A cross A. It's A valued because the P and the Q are A valued. So this is A valued. So you take in a vector field in A cross A, you calculate its values as they match up to a curve in A cross A, and it gives you back a number, back a value in the algebra. I have a suspicion that you could prove that partial Q partial W equal to partial P partial Z implies path independence of P comma Q with respect to this integration. Then we could define this function f by an integral like this. And really, see, I don't know.
I think I don't know. I think I'm just confused on what even R versus R cross R is.
R cross R?
Like, what's the difference between R and R cross R? Besides like a two variable component.
R cross R is the plane, R is just
A line, right?
line, yeah.
But the question is, we're going from a curve to a line, because we're going from A cross A into A. I don't even know what my question is, honestly. We're trying to get inputs, or outputs, right? Like single outputs. On this mapping, at least.
Oh, but I haven't finished this yet, right? This is all. For its worth. The reason I jumped over to here is we have theorems about like vector fields, P comma Q, right? That JMO. Ooh. Let's see. What would be nice? What would be nice is if, in the spirit of calculus 3, we could also write that this was equal to the integral over the curve of like P dz plus Q dw.
Elaborate. Was like what is
I don't think that's not an especially deep thing I just said, by the way. That's just, I wouldn't work.
is that because that integral straight out output F?
I mean, what I'm saying is it wasn't terribly deep, because you probably would define integral of P dz to be the integral of P of gamma T dz dt times dt, and the integral of Q dw would just be the integral of this dt. So like this is just another notation from what's above. That's, by the way, what's done in the real case. Like if you talk about the integral of P dx, it is the integral over curve. You know, you just do like P of, you parameterize, you know, the curve, and you do times dx dt, where x is the x component of the parameterization of the curve. Like this is what the PDX integral is, like literally just a piece of the line integral. Q dy is a piece of the line integral of, you know, p comma q dot dr. I'm thinking about what I'm puzzling about is how does this kind of integral over a cross a, can it drop back to just an integral over a? You know? I think it's the same issue we have in calculus 3. We have an integral of a function of two variables, and we're like, we can think of this just as an ordinary integral because one of the variables is frozen. Does that still make sense here?
I don't know. Calc 3 is like when I think of a curve in like 3 dimensions, you know, you parameterize it by the components, and then, but you know, there's also this underlying, you know, there's always a plane on which the curve lies, and so like that's how you could think about it, in like in an R2 sense. There's always a, what's it called? Well, not always. Because, like, you know, if you have a helicoid, there's no plane you could put a helicoid on. That would map the entire helicoid onto R2. But, like, you know, so it depends. I don't know. You have a simple curve. No, but I mean, it's still going in 3 directions. I mean, yeah, you can really get the whole thing. You can get the whole picture out of it. So it's kind of pointless.
I will say, I think for that formula, if we think about partial f, partial z, I do think we get that's the p of z naught comma w naught, like we want. Is from the goodness. goodness gracious, where was that? For me, it
Are you
was.
talking about the Q section? Yeah, the Q section is gonna do what we want, I'm pretty sure, just because that's how it worked out in the real sense.
So actually, theorem 10.12
Mm-hmm.
is where I finally get around to saying it. Page 50 of the introduction to the calculus paper
Yeah.
is where my FTC one is. But I actually think that it's not.
Yeah, the partial.
I think we can track through the derivation we had in Salas and Hilly.
Yeah, I think Q's gonna work out the same. It's really the P that I'm not too sure about. Because there's a lot of steps to get from P, you know, like we have to go through the net change, and then before that you have to, like here, like they, you know, so, you know, partial x integral of x naught to x spits out P of x y naught. And so so P of x y naught pops out, but how do you get P of x y to pop out? In this case, P of z w.
Oh, so yeah, that should give us P of z,
Or neta.
P of z comma w naught from the first term, right? And then, wait a minute, no.
The Q term will spit out
Yeah, partial z.
be fine, I think. Even like yeah, because I mean, I don't even think you have to do any funny algebra. I don't think there's any really funny algebra theorem you have to get dwd. Or yeah, so you know, you take a.
Oh yes, yeah, partial
Yeah.
q partial w should just spit out.
Yeah, this
this,
one's.
I got you.
Yeah, that's gonna work out. It's the P.
It's the p that, yeah, the p requires the, so we differentiate the p with respect to z.
And then you get spit out P of data W naught, but we need P of what, neta zeta or Z or W Z W. We're all over the place with this.
Huh.
So here we take our Q, we take that same thing, and when we partial differentiate it over the reals,
Oh, but I
we
need
can flip
to.
it. See, did we already prove?
No, what I need to check is that what I need is that p is partial f partial z,
Yeah.
and q is partial f partial w. I mean at the point at z comma w, of course. And
Yeah. Oh, I didn't even. Yeah, you do have to. How do we
So,
do it here?
if
We just
we-
assume.
If we differentiate with respect to w, then there's no w dependence here, so that gives us q of zw. Great, we've got q as partial f partial w. So that's the easy part, like you're saying.
Yeah.
Now,
Well, that's what we're starting with, though. Is that?
no, we're starting with partial q partial
Oh,
w
you're
partial
partial
z.
F. Ah.
So we need that f is as advertised, that it actually is a function whose gradient is p comma q. Gradient in this a cross a sense. But, so when we calculate partial f partial z, see there's a z dependence to both of these integrals.
Yeah. But how we get around that? Because that's going to split you out partial. The first term is going to get you p neta w naught.
Right.
No problem.
Z
Yeah,
but
yeah. The second part, you're gonna get hit with a partial z, right? Integrate partial z integral of w naught to w, and then it should be q of z zeta. use eta. And how we got around it in the real sense is we could flip.
Yeah, flip those.
Yeah.
And
then we prove that that's equal to that because of our assumption, because we're going backwards, and then it spits out net change. We have net change.
yeah.
Do we have that flips? If we have that flips the net change, then we can show off net change.
I think we should.
How do you prove that flips?
I think it goes back to the fact that it flips for real partial derivatives. I mean, I think again the real theorem we can steal to our current context by just recognizing that this differentiation is exactly a real partial derivative.
I feel like there's a sneakier way to do it.
But because this partial derivative is in fact a real partial derivative, we can use the order of integration and differentiation by the real theorem. And now that does, we do need to know that the function defined by the integral is a-differentiable in the first slot. I mean, the fact that Q is a-differentiable in the first slot, why does that imply that the integral of Q over zeta from W0 to W is still a-differentiable in the first slot? I mean, that's a reasonable claim, but why is that? If it is, then we can change this partial derivative, that this exists, and we can write it as the partial derivative with respect to the Cartesian coordinate corresponding to the unity in the algebra, and then we can apply the real theorem about swapping integration and derivatives.
I suggest the way we're gonna have to do it, because like I can't think of a way to rewrite partial z, because like we can sometimes with the song and dance of it being we can multiply it by some basis. So like if we took that as like if we were saying that the integral is like just any variable, we could say that what would we say? One second. That partial f partial xk is equal to dpf of vk now, and then it's partial f partial x1 times bj is equal to partial f partial xj. There's no way we can really rewrite that into a sneaky way to where the integral would flip sides.
Yeah, like I said, for that derivative to exist, it has to be equal to the partial derivative with respect to the unit in the first copy of A. So in summary, I do think that this formula still will work in A cross A, provided that we're given that the conditions are met in a set which allows these kind of line segments to be put between these two points. So, for example, if it's true on A cross A itself, we're good. Right? If there's like no, if it's an entire condition, so to speak. But I'm actually kind of interested about this integral over here. Like, what are the properties of that integral? What else can we say about that?